Hello, the Math Dog here. In this video I go over a proof of the Triangle Sum Theorem, which states that the sum of the interior angles of a triangle add up to 180 degrees in Euclidean geometry. I will talk briefly about Euclidean versus spherical geometry, because in spherical geometry you actually get a different result. The sum of the interior angles of a triangle actually could add up to even 270 degrees. So let's get started. So in Euclidean geometry, named after the Greek mathematician Euclid, who came up with 5 basic postulates for geometry or assumptions and derived many results from that. So we will show that the sum of the interior angles in this Euclidean geometry will add up to 180 degrees. In other words, you have a triangle ABC. The sum of the angles A plus B plus C will be 180 degrees. So in Euclidean geometry, we operate on a, quote, flat plane, unquote, like a tabletop. So very important to Euclid's geometry was his parallel postulate. So in this we will assume his parallel postulate to be true, which essentially stated, using my diagram here, for any line AB, and this is on a plane, for a point X not on that line, say here's point X not on AB, this X is not on AB, there exists exactly one line CD that passes through X and is parallel to line AB. Parallel means does not intersect. Okay, contrast that to spherical geometry. In spherical geometry, everything takes place on a sphere. Lines are great circles, so this would be a line in spherical geometry. This is a great circle. The sphere has a center, a diameter runs right through the center and touches 2 points on the sphere, analogous to the diameter of a circle. Now the interesting thing, at least I think so in spherical geometry, is you have here's 2 lines. They're like rubber bands around a ball. Okay, these are both great circles, and a great circle you can also think of as an equator around the Earth. Notice that there are no parallel lines because every line will intersect another line. And notice I have 3 lines here, the blue one, the black one, and the red one. These are all right angles here. These are 90 degrees. So the sum of these angles is not 180. It's actually going to be 270. So that's what I summarize here. There are no parallel lines. All lines intersect. The sum of the interior angles of a triangle can be 270. And that's all because in this geometrical system, we do not assume Euclid's parallel postulate. We do not assume that there's going to be exactly one line through a point not on a given line. So that assumption is dropped in spherical geometry. Well, anyway, let's get on to the proof of what we're trying to do here. So proof of the Triangle Sum Theorem. I've got 2 parallel lines AB. I'm giving you that right here in my givens. I have a triangle ABC. I'm going to prove that the measure of angle 2 plus measure of angle 4 plus measure of angle 5 has to equal 180 degrees. And that is what we're trying to prove. So we're going to start with our givens. I'm just going to list them together in the state, and I'll call this number 1, triangle ABC. And then I have line A is parallel to B, and I'm going to write that's given. Okay, now if you inspect, you notice here's 2 parallel lines. For example, this line right here, use a different color than black. This green line here that I'm outlining, that is a transversal, let's call it T, to these parallel lines. And because of that, the measure of angle 1 has to equal the measure of angle 4, because this transversal T cuts these parallel lines AB, and we have an alternate interior angles theorem which says if 2 lines are parallel, then the alternate interior angles are equal. And notice this is the interior of those parallel lines right here, and these angles are on opposite sides of the transversal. So I now can write that the measure of angle 1 equals the measure of angle 4. Okay. Likewise, I have another transversal right here that I'm outlining segment AB or line AB. That's angle 2 there. That's a little sloppy. Let's do that again. Okay, so notice I have Angles 3 and 5, those are alternate interior angles also, because here's the interior, they're on opposite sides of the transversal. So I know that those two angles, 3 and 5, are congruent to each other. Okay, so 1 and 4 are congruent, 3 and 5 are congruent because of the alternate interior angles theorem. Alright, so the reason there I'm going to give is alternate interior angles equal implies that lines are parallel, but I'm actually going to go a step further. In my video on corresponding angles and the theorems that follow, I talk about the biconditional statement. That means this reads true both ways. So it reads true if alternate interior angles are equal, assuming lines are parallel, then, I'm sorry, given that alternate interior angles are equal, then the lines will be parallel, okay? Likewise, you could read the converse, which is the opposite direction. That'd also be true. If lines are parallel, then the alternate interior angles are equal. And this is called a biconditional, which means the statement can be read both ways, both directions. And once I know that, I just like to use this so I don't have to keep changing. I just use this statement all the time. Okay, step 3. The purists may have a little trouble with me on this one, but notice that this is a straight angle right here. Okay, that's 180 degrees. Okay, that's the definition of straight angle. Notice that 1, 2, and 3 add up to 180 degrees. Okay, they're adjacent angles. Well, 1 is adjacent to 2. Adjacent means they share a common vertex, they don't overlap. 2 and 3 are adjacent angles. They share a common vertex A. They don't overlap. So I'm going to write the measure angle 1 plus measure angle 2 plus measure angle 3 equals 180 degrees. And I'm going to use the linear pair postulate. The purists may have some trouble with this, but I'm just saying, okay, so we define the linear pair postulate for 2 angles. Well, I should be able to do that for 3 angles as well, because they are supplementary when you put them all together. The supplementary technically just means 2 angles, but I could talk about 3 angles also adding up to 180 degrees. So I'm going to use that. And now my last step is, okay, measure angle 1 equals measure angle 4, so I can replace measure angle 1 here with 4. Measure angle 3 equals measure angle 5. I can replace measure angle 3 with measure angle 5. So my final conclusion here will be replacing 1 with 4. I had the measure angle 4 plus the measure of angle 2 plus replace 3 with 5. That has to equal 180. And the reason for this is I'm doing substitution. I'm replacing something with something that's equivalent to it. Technically, substitution property of equality, I'm just going to call it substitution. Okay, so in my proof I have measure angle 2 plus measure angle 4 plus measure angle 5 here. I just have them reversed. If you want to get technical, again, you could use the commutative property. 2 things equal A plus B equals B plus A, so I could just swap these out and add a step 5. I'm not going to do that, but this is the proof for the triangle sum theorem. So this theorem, this property comes from somewhere. It was logically deduced. It's not just someone decided that they're going to add up to 180. It actually follows from previous assumptions and theorems. So I hope this video was helpful. If you found it informative and you liked it, please give it a thumbs up and consider subscribing to my YouTube channel, The Math Dog. You may share the content of this video with others. Thank you very much and have a